Good day, everyone. Welcome to today's class, and we'll start immediately. We ended last class by talking about isotopes. I hope the lecture notes have been downloaded. The one for the last class, I hope you have found it on the LMS page and downloaded it. For today's class, I'm going to try and regulate the time we chat such that there will be less distraction. I hope you know that we keep a record of everything that happens in the class. It is automatically recorded, your chats are automatically recorded, and it's funny that some of us talk about things that have nothing to do with the class. So today, in about a minute's time, I'm going to have to mute your chats, then open it up when it is necessary to talk. The only reason why I would need you to respond is to know if you are hearing or following me. But I already have people around listening and they can inform me if the network is misbehaving or something else is happening. So apart from that, I will have to mute your chats. If you need to say anything urgent, just keep your hands raised. But if not, you can please bear with us today so that we can focus on what we have to do and not distract the class. Thank you. Please, there is no need to raise hands now. Thank you. So I'm going to start with isotopes and the relative atomic masses, just like we ended yesterday. Pardon me. Okay, so this was where we ended yesterday, talking about how to denote an atom of a particular element. The symbol of the element is written, and at the same time, we have the mass number that talks about the constituent of the nucleus. The constituent of the nucleus is termed nucleons, talking about the protons and the neutrons. And then we have the atomic number, which is the number of the protons or electrons in an atom. So we say that in an element, a sample of an element may contain atoms that have different atomic masses. They have the same number, different atomic masses. These are termed isotopes. Atoms of the same elements that have different atomic masses but have the same atomic number. And because they have different atomic masses, that means their number of neutrons is different. Example is what you have here, that of hydrogen. Hydrogen has 3 isotopes. We have proton, deuterium, and tritium. Proton, deuterium, and tritium. As you see in that table, each of them are the same number of electrons, the same number of protons, but differ in their number of neutrons. Proton, the first one, this one we normally call hydrogen, has no neutron. Deuterium has 1 neutron and tritium has 2 neutrons. their atom will look like what you have there. You can see the electrons, the one electron each on each of the atom. The electron is outside the nucleus, and the nucleus contains either the proton alone or the protons with the neutrons. Now, like we said, that the isotope of the same elements differ in the number of neutrons. But because the number of electrons, because the number of electrons are similar, and in any chemical reaction, nucleus is always intact. In a normal chemical reaction, the nucleus is intact. It's only the electrons that are involved. Or shared. So it is the electrons that get transferred. It is only in activity that you find the nucleus of an atom being affected. So electrons that I will repeat myself because I noticed that the network is unstable. So I will simply repeat what I just said. Don't worry, Favor. It's network from my end. I noticed that, so don't worry. You can put down your hand. I'm going to repeat what I just said in the last minute. I said, in a normal chemical reaction, electrons are the ones that are involved. Is it that electron is lost or gained? That's a normal chemical reaction. But in radioactive, anything that has to do with radioactivity, those are nuclear reaction, nuclear from the word nucleus. So it is only in radioactivity that the nucleus of the elements of the atom is affected. Therefore, isotopes have similar chemical properties because the chemical properties is determined by the electronic structure from the word electron, from the electronic structure. So you can see electrons from electronic. So since they have the same number of electrons, and it is electrons that determine the chemical properties and how a particular element will behave in a chemical reaction. Therefore, isotopes have similar chemical properties. For example, they may ask you, we have different isotopes of oxygen and that of carbon. So if you have CO2 from different isotopes of oxygen and carbon, will they react the same way? The answer is yes. Because the chemical structure, chemical property is determined by the number of electrons. So it is now imperative for us to know how much of each isotope is in a sample of an element. For example, you can have, like we have that oxygen as proton, as deuterium, as tritium. If you have a sample of oxygen, it will have a percentage of each of these isotopes. Some of that may be very minute, minimal, maybe 0.000 something percent, whereas one will be like 90 something percent. But we cannot assume once we have those elements that has isotopes, we can't assume that we have only 100% of a particular type of isotope in a sample. So we need to be able to differentiate between the isotope of this element and know their relative abundances, how much of each is present. This is where a mass spectrometer comes in. It is a device that is used to determine, number one, the relative atomic or relative molecular mass of an atom or a molecule. It is used to determine the relative atomic mass or relative molecular mass of, of an atom or molecule, and it can also be used to determine what isotopes are there and what is their abundance, how much of each of the isotopes is present. So in the next few slides, we are going to be briefly talking about the operation of a mass spectrometer, see how it sample inside it, how it is able to measure the mass. Now it shows its result in as a mass to charge ratio. So I will show you in a bit now. This is a typical mass spectrometer. You can find it's varied. You can find a smaller version of this, but it's actually it's usually concerned with its operation. The operation of a mass spectrometer is usually the same. So this diagram is what we are going to use to explain the operation of a mass spectrometer. The diagram we are going to use today. So I want you to look at this diagram very well and just talk briefly. I'm sure when you begin to do chemistry 176, for those that are still going to offer organic chemistry in 100 level, you would be taught in detail. But for our for 156, we just use it to explain how we can determine the isotopes briefly. So we start with the ionization chamber, or sorry, vaporization chamber. The sample enters and gets vaporized because we can't use a solid sample. We start with a vaporized sample. So we have a vaporization chamber where the material to be analyzed is injected and heated until it vaporizes. That is, it changes to a gaseous form. Then, oh, sorry about that. Chamber. Here, the vaporized chamber, as the vaporized sample is bombarded with electrons from an heated filament. When you do that, electrons are knocked off. Remember, we are going to put a sample of an element here. We are expecting that the element is going to be a neutral, the element. When it gets neutral, you're not putting a charged element or atom there. So when you put the atom, the element gets there, the atoms get vaporized, and when it is heated, electrons are knocked off. So sometimes you have one electron gets knocked off, or two electrons get knocked off. This will also depend on how many electrons are in the outer shell of that particular element or atom. So when electrons are knocked off, you have a positive ion formed. You- the atom becomes positively charged. That means it has a residual number of protons. Usually, we have equal number of electrons and protons. Electrons are negatively charged, protons are positively charged. So when you remove, let's say, one electron, so the atoms becomes plus one. It has a residual positive, one positive charge. So if it is two electrons that are knocked off, that means the number of, if you look at the number of electrons versus protons, you have two more protons. That's why it is plus two. You have two more protons than the electrons. So whatever it is, you have positively charged
Hello.
Just to unmute.
I'm waiting to happen here.
Goodness, how far now? Goodness. Goodness, what's going on by? What did they do? I said, no, they didn't declare visitor. Ah, no, they do. Hello. Hello.
Adoye, Oluwabamide, dey stop it now.
Great.
What's going on?
Omiwa Kosi, Omiwa.
Everybody, what's
But what's she?
I'm really sorry. I half of the class is already gone. I've been trying to battle with my